In 1982, a sponge diver named Mehmet Çakır stumbled upon a pile of strange, flat ingots resting on the seabed off the coast of Kos, Turkey. These ingots were not gold, they were not silver, they were copper, 10 tons of it, stacked in the hold of a ship that had gone down more than 3,000 years earlier. A routine dive off Uluburun had just uncovered one of the largest and most significant Bronze Age maritime discoveries in history. The cargo proved that Mediterranean trade networks in 1300 BCE were not primitive barter systems. They were industrial-scale operations capable of moving vast quantities of strategic metal across open water. The ship had been carrying enough copper to forge an entire arsenal of bronze weapons. This is where the story takes a turn nobody expected. That copper was not the beginning of humanity's relationship with the metal. Not even close. The true origin point lies nearly 7,000 years further back in time. Chilean Tepesi, a settlement mound in the upper reaches of the Tigris River basin in what is now southeastern Turkey. Archaeologists excavating the site in the late 1960s and early 1970s pushed down through layer after layer of human habitation. They uncovered a sequence of round pit houses and later rectangular structures built from mud brick and stone. The deep layers dated to the pre-pottery Neolithic period, roughly 8,700 years before the Common Era. The inhabitants of Chilean were not yet farmers in any systematic sense. They lived somewhere in the blurred transition between hunting and herding, between gathering wild grains and deliberately planting them. And among the flint blades and animal bones and grinding stones, the excavators found something else. Tiny beads of native copper, flattened and rolled into simple tubes. Pins and awls hammered from small nuggets picked up from riverbeds or pried from surface outcrops. The people of Chilean had not invented smelting. They were not heating ore in a furnace to extract liquid metal. They were simply collecting naturally occurring chunks of almost pure metallic copper and hammering them cold. But they recognized something essential about the material. It was malleable in a way that stone was not. It did not shatter when struck at the wrong angle. It could be bent and shaped without breaking. A crude copper awl could pierce leather more reliably than a sharpened stick. A copper bead caught the light in a way that simple shell or bone never could. The Neolithic mind had found its first artificial material. For the next several thousand years, small communities across the Near East and southeastern Europe repeated the same discovery. They found copper in stream beds and on rocky hillsides. They picked up the dull green and blue-green oxidized lumps and experimented with them. And gradually, probably by accident near a kiln or a hot campfire, someone discovered that heat transformed the metal. Heating native copper softened it, making the hammering easier. Heating copper-rich rocks with charcoal produced something entirely new. A glowing trickle of liquid metal could be separated from the surrounding rock and cast into a mold. The Chalcolithic Age had begun. The Varna necropolis in modern Bulgaria provided the most stunning evidence of what this shift meant for human society. In 1972, a construction crew digging a trench near the Black Sea coast uncovered a burial ground that dated to roughly 4,500 BCE. The excavators who followed found 294 graves spread across the site. Most contained modest burials, with a few clay pots and simple ornaments. But 47 of the graves were different. These were the graves of a ruling elite, and the objects buried with them rewrote the history of metallurgy. Scepters with gold fittings, solid gold discs and bracelets, and among the gold, a wealth of copper. Heavy copper axe heads, their edges sharp and precise. Copper chisels and awls, refined far beyond the simple hammered beads of Chilean. Long copper pins that once fastened elaborate ceremonial garments. The Varna copper was not just functional, it was a statement. The people buried in those graves had controlled access to the world's most advanced technology. A metal that came from the earth, transformed by fire, shaped into tools and weapons that no stone implement could match. The social structure of Neolithic Europe was fracturing under the weight of this new material. Those who controlled the copper controlled the power. The pattern repeated again and again as the knowledge of smelting spread. One discovery, frozen in alpine ice for more than 5,000 years, provided the most intimate look at the Copper Age world. On September 19, 1991, two German hikers in the Ötztal Alps, near the border between Austria and Italy, spotted a human body emerging from a melting glacier. They assumed it was a recent mountaineering victim. It was not. The body belonged to a man who had died roughly around 3,300 BCE. The ice had preserved his clothing, his equipment, and his weaponry in extraordinary detail. He carried a bow and a quiver of arrows, a flint knife with a wooden handle, a birch bark container for carrying embers, and a copper axe. The axe blade was the critical artifact. Scientific analysis revealed it was 99.7% pure copper. The metal had been smelted from ore, poured into a mold, and then carefully cold-worked and polished to a gleaming edge. The copper itself was not local to the Alps. Chemical sourcing traced the metal back to ore deposits in southern Tuscany. The Ötzi axe proved that by the late 4th millennium BCE, copper was moving across Europe in established trade networks. Bronze was harder than copper. It held an edge better. It flowed more smoothly into complex molds, allowing craftsmen to cast intricate shapes that pure copper could never achieve. And it was the metal that would give its name to an entire epoch of human history. The Bronze Age collapsed the old Neolithic order across the eastern Mediterranean, the Near East, and beyond. Armies equipped with bronze swords and bronze spear points destroyed enemies armed with stone. Kingdoms that controlled bronze production and trade grew wealthy and powerful. Those that lacked access to copper and tin became dependent on those that did. And no place in the ancient world was more central to copper production than the island of Cyprus. The relationship between the island and the metal was so intimate that the word copper itself was born there. The Latin term for the metal was as cyprium, metal from Cyprus. Over centuries, the phrase contracted in common speech to cuprum. From cuprum came the English word copper. The island's deposits of copper ore were among the richest in the Mediterranean. The mines of Cyprus, worked by slave labor and controlled by powerful local kings, fed the insatiable demand of the great Bronze Age empires. Egypt needed bronze for weapons and tools and the construction of monumental architecture. The Hittite Empire in Anatolia built its military dominance on bronze chariots and bronze swords. The Mycenaean Greeks, the Minoans on Crete, the city-states of the Levant, all of them depended on copper shipped from Cyprus. The Uluburun shipwreck provided the most vivid snapshot of this trade in motion. The vessel was a small cargo ship, perhaps 50 feet long, built from cedar planks and powered by a single square sail. It had departed from the coast of the Levant, carrying a cargo of staggering value and variety. Ivory from elephants, hippopotamus teeth, glass ingots colored deep cobalt blue and brilliant turquoise, cylinder seals from Mesopotamia, gold and silver jewelry, weapons and tools, foodstuffs including almonds, figs, olives, and pomegranates, and the core of the cargo, 10 tons of copper ingots. The ingots were mostly cast in the distinctive oxhide shape, a rectangular form with 4 projecting corners, easy to stack and secure in a ship's hull. There were 354 copper ingots on board. They came from multiple sources, including Cyprus, confirming the island's role as the primary supplier. Some ingots were also sourced from deposits in the Timna Valley and elsewhere, indicating complex supply chains. The ship also carried roughly 1 ton of tin ingots. The tin was the rarer and more valuable component of the bronze equation. Its source remains a mystery. The major tin deposits of the ancient world were in Cornwall, in far western Britain, and in Afghanistan. How tin from distant regions reached the Mediterranean workshops that needed it is one of the enduring puzzles of the late Bronze Age. The Uluburun ship sank around 1300 BCE. It was found lying at a depth of roughly 44 to 61 meters, its hull long rotted away, its cargo scattered across the sloping seabed. The sponge diver who first spotted the ingots in 1982 had no idea what he was looking at. He brought a piece of metal to the surface and showed it to archaeologists. They recognized the distinctive oxhide shape immediately from ancient Egyptian wall paintings and temple reliefs. The excavation of the wreck took place over 11 seasons between 1984 and 1994. It was directed by George Bass and later by Kemal Pulak of the Institute of Nautical Archaeology. The team used a grid system and underwater vacuum lifts to carefully excavate each layer of cargo. Every artifact was mapped, photographed, and catalogued. What emerged was the most complete picture ever obtained of a Bronze Age trading vessel and its cargo. The copper ingots that had sat on the seafloor for more than 3,000 years were chemically analyzed. The isotopic signatures of the copper pointed to multiple ore sources. Cyprus was confirmed as the main contributor. But the analysis also revealed trade networks far more sophisticated than any written record of the time had suggested. Copper was moving across the entire eastern Mediterranean in quantities that implied organized, institutionalized commerce. The ingots were not random private cargo. They represented the economic output of state-controlled mining operations. The kingdoms that mined the copper, shipped the copper, and forged the bronze held enormous power. But that power had a fatal weakness. The entire Bronze Age system rested on two metals that few regions possessed. When the supply chains broke, the system collapsed. Around 1200 BCE, a cascade of disasters struck the civilizations of the eastern Mediterranean. The causes are still debated. Earthquake storms, climate shifts that brought drought and famine, mass migrations of peoples the Egyptians called the Sea Peoples, who attacked coastal cities and destroyed trade routes. Invasion and internal rebellion. The Hittite Empire fell. The Mycenaean palace kingdoms of Greece collapsed. The cities of the Levant were sacked and burned. Egypt survived, but was permanently weakened. The trade in copper and tin, the lifeblood of the Bronze Age economy, disintegrated. Without tin, there was no bronze. Without bronze, there were no weapons to defend the palaces. Without trade, the complex interdependent structure of the eastern Mediterranean world simply stopped functioning. The written records of the Hittites fell silent. The scribes in Mycenaean Greece stopped recording grain shipments on their clay tablets. The palaces were abandoned. The great network that had moved 10 tons of copper across the sea on a single ship unraveled completely. The Uluburun ship had sailed at the peak of the Bronze Age system. It carried the metal that built empires. The empires that depended on that metal did not survive its collapse. And for centuries after the fall, the art of large-scale copper production and long-distance metal trade remained diminished. The bright promise of the Metal Age had ended in darkness. The question of where the tin came from, the missing half of the bronze equation, remains unanswered to this day. Geologists and archaeologists have proposed sources from Cornwall to Central Asia. The mystery endures because the scale of the trade implied by the Uluburun cargo was huge. Somewhere in the late Bronze Age, ships were carrying tons of tin to Mediterranean ports. The mines and the routes and the merchants who handled that trade left almost no trace. The bronze itself was melted down, reforged, recycled over and over for centuries. The copper ship sank. The copper ingots sat in darkness at the bottom of the sea for more than 3,000 years. The empires that forged them had vanished. The writing systems that recorded their transactions were forgotten. The technology that produced them was lost and then reinvented. The metal itself remained unchanged. When sponge diver Mehmet Çakır held a piece of that cargo in his hand in 1982, he was holding a direct physical link to an age when a single metal could determine which civilizations thrived and which crumbled into ruin. Copper had built the Bronze Age world. It would eventually build another world entirely. A world wired for electricity, powered by grids, connected by instant communication across oceans. That new world required more copper than the ancients could have imagined, and the price of extracting it would be paid in ways the Bronze Age miners of Cyprus never could have foreseen. The streets of Butte, Montana ran thick with mud and money in the summer of 1899. Miners descended into the shafts at dawn and emerged at dusk covered in red dust. The hill beneath the town held more copper than any single deposit ever found on American soil. 3 men controlled it. William A. Clark arrived in Montana during the gold rush of the 1860s and built a banking empire before turning his attention to mining. Marcus Daly was an Irish immigrant who had worked the Comstock lode in Nevada and knew ore bodies the way a surgeon knows anatomy. Fritz Augustus Heinze was younger, brasher, the son of a wealthy New York family who came west looking for a fortune and found one. Their fight for Butte's copper would reshape the American electrical grid and determine who lit the cities of the 20th century. The war began underground, with miners working adjoining claims, blasting through rock and sometimes through each other's tunnels. It continued in courtrooms, where lawyers argued over the Apex Law, a federal statute from 1872 that governed mining claims. The law stated that a miner who struck a vein on his property had the right to follow that vein wherever it led, even if it crossed under a neighbor's property line. Hines exploited this law with surgical precision. He bought small surface claims adjacent to the massive Anaconda holdings controlled by Daly and later by Standard Oil interests. Then his lawyers argued that the richest veins running beneath Butte Hill actually apexed on Hines's tiny parcels of land. The legal battles consumed years. Judges were elected, and judges were bought. The Montana state legislature passed laws aimed directly at breaking Hines's stranglehold on the court system. At one point, Clark owned a newspaper, the Butte Miner. Daly owned the competing Anaconda Standard. They fought their battles in print as fiercely as they fought them underground. The copper that came out of Butte fed a hunger that had been building for nearly a century. The hunger began not in a mine shaft, but in a lecture hall in Copenhagen. In the spring of 1820, a Danish physicist named Hans Christian Ørsted prepared a demonstration for his students. He placed a compass needle near a wire and connected the wire to a battery. When the current flowed, the needle deflected. The needle moved every single time he closed the circuit. Electricity and magnetism were connected, and Ørsted had just proven it in front of a room full of university students. The implications took years to sink in. If an electric current could move a needle, an electric current could carry a signal. And if a current could carry a signal, information could travel faster than a horse or a ship or a train. The world needed a metal that could carry that current with as little resistance as possible. Copper was the answer. Silver conducted electricity slightly better, but silver was rare and expensive. Gold resisted corrosion, but cost far too much for any practical application. Copper was abundant, relatively cheap, and extraordinarily conductive. No other non-precious metal came close. In 1837, two Englishmen named William Fothergill Cooke and Charles Wheatstone patented the first commercial electrical telegraph. Cooke was a former army officer who had seen a demonstration of an early telegraph prototype in Germany and returned to England obsessed with the idea. Wheatstone was a physicist who had been experimenting with electricity and sound at King's College London. Together, they built a system that used 5 needles to point at letters on a diamond-shaped board. The first operational line ran between Euston and Camden Town, along the railway tracks of the London and Birmingham Railway. It was less than a mile and a half long. The railway companies saw the value immediately. Trains could be signaled, schedules coordinated, accidents avoided. Within a decade, telegraph lines strung with copper wire spidered across the British countryside and began crossing under the English Channel toward France. The Atlantic Ocean was next. By 1858, the first transatlantic telegraph cable connected Ireland to Newfoundland. It was insulated with gutta percha, a rubber-like sap from trees in Southeast Asia, and wrapped in copper conductors. The first message from Queen Victoria to President James Buchanan took 16 hours to transmit. The cable failed within weeks. Engineers laid a more durable replacement in 1866, and the Atlantic Ocean was crossed for good. Copper wire now connected continents. The demand multiplied with every mile of cable laid. Mines in Cornwall that had produced tin since the Bronze Age shifted to copper. The Chilean deposits in the Atacama Desert drew British investment and new smelting technology. The Michigan Copper Country on the Keweenaw Peninsula sent pure native copper straight from the mines to the factories. And then, a young inventor in Menlo Park, New Jersey, changed the equation entirely. Thomas Edison did not invent the electric light. Inventors had been experimenting with incandescent filaments for 50 years before he arrived. What Edison did was build a system. He tested thousands of materials for the filament until he settled on carbonized bamboo fiber. He designed a vacuum pump that could evacuate air from the glass bulb more efficiently than any previous device. He built generators, switches, fuses, junction boxes, and meters. And most critically, he understood that a light bulb was useless without a network of copper wires to deliver power to it. On September 4, 1882, Edison threw the switch at the Pearl Street station in Lower Manhattan. A single steam engine drove a generator nicknamed Jumbo. Direct current flowed through underground copper cables to 59 customers in a 1-square-mile district of the financial center. The cables ran inside iron tubes buried beneath the cobblestone streets. Each building required its own branch circuit, its own copper conductors, its own insulated wiring snaking through walls and ceilings. The age of the electrical grid had begun in a single square mile of New York City. The scale of copper consumption was about to explode. A single power station required tons of copper cabling just to distribute electricity a few blocks. Multiply that by every city in America and every city in Europe, and the numbers became staggering. The mines of the world raced to keep up. Arizona's copper deposits opened at Bisbee and Jerome. The Kennecott mine in Alaska shipped ore so rich that miners joked it came out of the ground already halfway to wire. And in Butte, Montana, the war underground intensified. Marcus Daly had discovered the Anaconda vein in 1881, a deposit of copper ore so massive that it turned his mining company into an industrial giant. The Anaconda Copper Mining Company built a smelter in the town of Anaconda, 26 miles from Butte, to process the ore. The smelter's smokestack rose 585 feet into the Montana sky, the tallest masonry chimney in the world at the time. William A. Clark, not to be outdone, built his own smelter and expanded his own mining operations. Clark's United Verde mine in Jerome, Arizona, produced copper, gold, and silver in quantities that made him one of the richest men in America. He used his wealth to buy a seat in the United States Senate, a purchase so blatant that the Senate itself investigated him for bribery. He served one term anyway. Fritz Augustus Heinze played a different game. He knew the Anaconda Company wanted to consolidate every square inch of Butte's mineral rights under a single ownership. Heinze bought the scraps nobody else wanted, the odd-shaped parcels, the claims that seemed played out. Then he found veins on those properties and argued in court that the big veins under Anaconda's land actually began on his. He won more often than he lost. Montana judges, many of them elected with the help of mining money, frequently ruled in his favor. The Anaconda Company responded by shutting down operations, throwing thousands of miners out of work, and blaming Heinze for the disruption. The tactic worked. Public opinion turned. The state legislature passed a change to the venue law that stripped Heinze's preferred judges of jurisdiction over mining cases. Heinze sold out in 1906 for roughly $10.5 million. The Anaconda Copper Mining Company absorbed his holdings and became the undisputed ruler of Butte. By 1910, Anaconda controlled the most productive copper district on the planet. The copper from Butte wired the cities of America. It carried telephone signals through the bell system. It distributed electricity from the generating stations of the growing grid. It wound through the armatures of electric motors in factories, streetcars, and elevators. The skyscrapers rising in New York and Chicago required copper for their electrical systems, their plumbing, their elevator cables, their communication networks. The First World War consumed copper at a rate no one had predicted. Every shell casing, every cartridge, every field telephone, every mile of communication wire on the Western Front required copper. The mines of Butte ran at full capacity through the war years and into the boom that followed. The Anaconda Company built a new smelter, opened new shafts, and deepened existing mines to follow the richest veins. Miners worked in shifts around the clock. The town of Butte grew to more than 60,000 people at its peak, packed into a narrow valley beneath the headframes of the mines. The streets glowed at night with the lights of saloons, boarding houses, theaters, and union halls. But the cost was already visible to anyone who cared to look. The smelter at Anaconda released arsenic-laden smoke that denuded the surrounding hillsides of vegetation. The soil for miles around turned gray and sterile. The miners who worked underground breathed silica dust and developed silicosis at rates that shortened lives and broke families. The hill beneath Butte was being hollowed out, and the company that owned it was becoming one of the most powerful corporations in American history. The War of the Copper Kings was over. William A. Clark died in 1925 in a mansion on Fifth Avenue in New York City. His art collection became the core of the Corcoran Gallery in Washington. Marcus Daly had died earlier, in 1900, before the war he started had fully played out. Fritz Augustus Heinze lost his fortune in a banking panic in 1907 and died of cirrhosis of the liver at the age of 44. The Anaconda Company continued mining. It expanded into Chile in the 1920s, buying the Chuquicamata deposit, the largest known copper ore body in the world. The pattern that had played out in Butte would play out again in the Atacama Desert. The company extracted the metal, the profits flowed north, and the land and the people bore the cost. The copper that came from Butte and Chuquicamata carried the current that powered the 20th century. Every light switch, every radio, every telephone, every electric motor contained a piece of that red metal. The electrical grid that had begun as a single square mile of copper cable beneath lower Manhattan now spanned continents. Generators turned, transformers hummed, current flowed, and somewhere beneath the streets of every electrified city on Earth, copper wire carried the energy that made modern life possible. The metal that had built the Bronze Age had built another world entirely. But the price of that world was still being paid. The hill in Butte kept giving up its copper. The miners kept going underground. The smoke from the smelter kept rising. And the pit that would eventually swallow the heart of the town was already taking shape beneath the headframes and the hoist houses. The Anaconda Company could not see it yet. Nobody could. But the copper that wired the world had already set in motion a reckoning that would leave a scar visible from space. In November 2016, several thousand snow geese descended on the Berkeley Pit in Butte, Montana. The birds landed on the water to rest during their migration. Within hours, they were dead. The water they touched had a pH of roughly 2.5. That is more acidic than lemon juice and more acidic than car battery acid. The pit dissolved the birds from the inside out. Their bodies were so laden with toxic metals that disposal crews had to handle them as hazardous waste. This was not a natural disaster. This was a copper mine. The Berkeley Pit opened in 1955 as a massive open-pit operation run by the Anaconda Copper Mining Company. The open-pit method was brutally efficient. Enormous trucks hauled ore up spiraling roads carved into the walls of the growing hole. By 1982, when Atlantic Richfield Company suspended operations, the pit measured roughly a mile across and 1,700 feet deep. Then the pumps stopped. Underground, a vast network of tunnels and shafts had been continuously drained for decades by powerful pumping stations. When Atlantic Richfield shut those pumps down, groundwater began flooding the abandoned workings. The water picked up arsenic, cadmium, zinc, copper, and sulfuric acid from the exposed rock. It rose through the old tunnels and seeped into the bottom of the pit. The Berkeley Pit became a toxic lake. Today, the water level rises about 1 foot per month. It now holds roughly 45 billion gallons of acidic, metal-laced water. The pit is designated a Superfund site by the United States Environmental Protection Agency. It is one of the most toxic bodies of water on Earth. But the Berkeley Pit is only the most visible scar. The full cost of copper extraction stretched across hemispheres and generations. The same patterns that hollowed out Butte had already repeated themselves in the deserts of northern Chile. The Chuquicamata deposit sat in the Atacama Desert at an elevation of over 9,000 feet. It was the largest known copper ore body in the world. The indigenous Atacameño people had extracted copper from surface outcrops for centuries before any European arrived. They used the metal for tools, for ornaments, and for trade. The Spanish colonial authorities took note of the deposit early. Small-scale mining began in the 1700s under Spanish rule, but the real transformation started in the early 20th century. An American company called the Chile Exploration Company, backed by the Guggenheim family of New York, bought the rights to Chuquicamata in 1912. The company built a modern mining operation in one of the most inhospitable environments on the planet. Temperatures in the Atacama swung from freezing at night to blistering heat during the day. No rain fell for years at a time. Workers lived in company towns constructed beside the pit. The company dictated their wages, their housing, their water supply, and their medical care. The copper they extracted flowed north to the United States and Europe. The profits flowed north with it. Chilean workers and the Chilean state saw comparatively little of the wealth their land produced. This arrangement persisted through decades of political turmoil, economic crisis, and growing labor militancy. The workers at Chuquicamata organized unions. They struck for higher wages and better conditions. The company pushed back. The Chilean government, for most of the 20th century, sided with the foreign-owned mining companies. Then came the presidential election of 1970. Salvador Allende, a socialist physician and career politician, won a narrow plurality of the vote. He campaigned on a promise to nationalize Chile's copper industry. The copper mines, he argued, were the backbone of the Chilean economy. Foreign corporations had extracted the wealth for more than half a century. The nation had a right to reclaim what lay beneath its own soil. On July 11, 1971, the Chilean Congress voted unanimously to approve the nationalization of copper. Allende signed the law 5 days later. The state took control of Chuquicamata, El Teniente, and the other major copper deposits. The foreign companies were compensated for their claimed investments. But the Chilean government deducted what it described as excess profits earned by the companies over decades of operation. The deduction was so large that the book value of the compensation fell to zero. The companies received nothing. Anaconda, which had owned Chuquicamata since the 1920s, declared the nationalization a confiscation. Kennecott, which owned El Teniente, filed lawsuits in courts across Europe to prevent Chile from selling its copper. The Nixon administration in Washington viewed Allende's actions with alarm. The United States had significant economic and strategic interests in Chilean copper. American companies had invested hundreds of millions of dollars in the mines. The nationalization threatened not only corporate profits, but also a Cold War strategic calculation. The establishment of a socialist government that expropriated American assets set a precedent that Washington could not accept. Declassified documents later revealed that the Nixon administration worked actively to undermine Allende's government. Economic pressure tightened. The United States cut off credits and loans to Chile through international financial institutions. The CIA funded opposition media, political parties, and labor groups. The copper that Allende had nationalized became difficult to sell on international markets. Spare parts for the mining equipment were hard to obtain because American companies controlled the supply chains. The mines themselves began to suffer from deferred maintenance and declining productivity. Chile became increasingly isolated economically. In September 1973, a military coup led by General Augusto Pinochet overthrew the Allende government. Allende died in the presidential palace as it was bombed by the Chilean Air Force. Pinochet established a military dictatorship that would rule Chile for the next 17 years. The Pinochet regime did not return the copper mines to their previous owners. The mines remained in state hands under a new entity called Codelco, the National Copper Corporation. But Pinochet opened the country to new foreign investment in copper exploration and extraction. Private mining companies returned to Chile under terms favorable to investors. The state kept the historic mines. Private capital developed new ones. Escondida, a massive copper deposit in the Atacama Desert, was discovered in 1981. It began production in 1990 under the ownership of a consortium led by the Australian company BHP Billiton. Escondida eventually surpassed Chuquicamata as the world's largest copper-producing mine. Chile became the dominant copper producer on the planet, supplying roughly 1/3 of the world's copper. Codelco alone produced about 10% of global supply. The metal from those Atacama mines fed the accelerating electrification of the global economy. By the early 21st century, copper had become indispensable in ways that Ørsted, Cook, and Wheatstone could never have imagined. Every personal computer contained roughly 1.5 pounds of copper. Every smartphone contained copper in its circuit boards, its wiring, and its battery connections. Every kilometer of high-voltage transmission line required hundreds of kilograms of copper cable. The internet ran on copper before it ran on fiber optics. And even fiber optic cables required copper sheathing for protection and grounding. Copper was the most conductive non-precious metal on the periodic table. Only silver surpassed it, and silver was far too expensive for industrial-scale electrical applications. Copper was the compromise that made the modern world possible. The International Copper Study Group reported that roughly 65% of global copper consumption went into electrical applications. Power cables accounted for the largest share. Electronics and telecommunications consumed much of the rest. The numbers were staggering in their scale. Global copper production in 2023 exceeded 22 million metric tons. Chile alone produced more than 5 million tons. The red metal flowed from the Atacama, from Peru, from the Democratic Republic of Congo, from the reopened mines of the western United States. It traveled in container ships and on rail cars to foundries and wire mills in China, in Germany, in Japan, and in South Korea. It emerged as winding wire for electric motors, as bus bars for substations, as printed circuit board traces, and as the miles of cable that snaked through the walls of every new building on Earth. Then the electric vehicle revolution began, and the demand for copper accelerated beyond any previous projection. A conventional internal combustion engine vehicle contained roughly 50 pounds of copper. A battery electric vehicle contained roughly 180 pounds. The difference was the motor, the inverter, the high-voltage wiring, and the charging system. A fully electric transit bus required more than 800 pounds of copper. The charging infrastructure required copper on an even larger scale. A single fast charging station for electric trucks drew enough current to require thick copper bus bars and heavy-gauge cable. The International Energy Agency projected that copper demand from electric vehicles and charging infrastructure would multiply several times over between 2020 and 2040. The metal that had wired the first telegraph, the first light bulb, and the first power grid was now essential to decarbonizing the global economy. But the deposits that supplied this demand were finite. High-grade ore bodies were becoming harder to find. New discoveries tended to be in remote locations with difficult geology, scarce water, and weak infrastructure. The average grade of copper ore mined globally had been declining for decades. More rock had to be moved, crushed, and processed to produce the same amount of metal. More energy went into extraction. More waste rock piled up on the surface. More tailings ponds contained the residue of the chemical processing. The Berkeley Pit in Butte was only one of thousands of legacy sites. Across the American West, across the Andes, across the copper belts of Africa and Southeast Asia, abandoned mines leaked acid drainage into rivers and aquifers. Tailings dams failed. In 2019, an iron ore tailings dam in Brazil collapsed and killed 270 people, burying a town in toxic mud. Copper tailings dams had failed before that and would fail again. The cost of conductivity was being paid in human lives and poisoned watersheds. The labor conditions in copper mining remained punishing. In the Democratic Republic of Congo, artisanal miners dug copper and cobalt from hand-dug tunnels with no safety equipment and no ventilation. Children worked the sorting piles. The metal they extracted entered the global supply chain through intermediaries and refiners. It ended up in the batteries and wiring of electric vehicles marketed as clean and sustainable. The tension at the heart of copper's story was inescapable. The metal that enabled the electrical revolution also scarred the landscapes from which it was taken. The fastest route to a decarbonized future ran through open pits, acid leach pads, and smelters belching sulfur dioxide into the atmosphere. The energy transition could not happen without copper, and copper could not be extracted without consequences. The Anaconda Company no longer existed. It was absorbed by Atlantic Richfield in 1977. The corporate entity that had dominated Butte and controlled Chuquicamata dissolved into a maze of mergers, acquisitions, and environmental liability claims. But the system it had created continued. Codelco, the Chilean state copper company, remained one of the largest industrial enterprises in the world. The Chinese state-owned mining companies, including companies like Zijin Mining and China Minmetals, had become major players in global copper extraction. The pattern that had begun in Butte and spread to Chuquicamata now played out across the developing world. Capital flowed from consumer nations into resource-rich but capital-poor countries. The copper came out. The profits migrated elsewhere. The environmental damage stayed in the ground and in the water. Butte, Montana still lived with the legacy. The Berkeley Pit was slowly filling. At the current rate, the water would reach the natural groundwater level around 2023. After that, the flow could theoretically reverse. Contaminated water from the pit could begin pushing outward into the surrounding aquifer. The EPA operated a water treatment plant on the site. Pumps extracted the toxic water before it could migrate. The treated water was discharged into a nearby creek. The plant would need to operate essentially forever. There was no end date for the treatment. There was no plan to make the pit safe. There was only containment, monitoring, and the hope that the funding would never run out. The snow geese did not know any of this in November 2016 when they descended out of the sky. They saw water in a dry landscape. They landed, and the pit that copper built claimed them in a matter of hours. The metal that wired the world had never been neutral. It had been extracted by slaves, by exploited laborers, by corporate armies, and by state-owned enterprises operating under every political system humans had devised. It had built fortunes and toppled governments. It had connected continents and poisoned watersheds, and the world was about to demand more of it than had ever been mined in the whole of human history. The next chapter of copper was not being written in Butte or Chuquicamata. It was being written in the lithium-rich salt flats of Bolivia, the cobalt pits of the Congo, and the nickel mines of Indonesia. The energy transition needed metals, and the mining of those metals was already displacing communities, draining aquifers, and cutting into the last intact ecosystems on the planet.